So people are getting into the room right now. So so Nathan, good to see you. So I don't think we met before, but it's good to I heard a lot of great work from you. So
yeah, nice to meet virtually.
are getting into the room right now. So
we
so
are.
Nathan, good to see you. So I don't think we met before, but it's good to I heard a lot of great work from you. So
yeah, nice to meet virtually.
are getting into
All right, so
right
we
now.
are
So,
live on you. We are
Nathan,
live.
good to see you. So I don't think we met before, but it's good to I heard a lot of great work from you. So
Nice to meet virtually.
are getting into
All right, so we are live on you. We are live.
Nathan, good to see
Can
you.
you ask people to mute because it's very noisy, except the speaker?
Nice to meet virtually.
All right, so we are live on you. We are live.
Good to see
Can
you.
you ask people to mute because it's very noisy, except the speaker?
All right, I'm going to let everyone in. We're going to start recording, and then you guys can start the presentation.
Would you like me to get started, Steve?
Yes, I think that let me just do a very quick introduction. So thank you everyone for the section 1 of the MLSE. So this is the first sections, and in these sections, our first speaker will be Nathan Trax, senior member of technical staff at Sandia National Lab. The title of this talk would be Data-Driven Exterior Calculus, Exact Treatment of Physics in Scientific Machine Learning. So thank you, Nathan.
Okay, thank you very much. Just get this set up here. Okay, so thank you very much for the invitation. What I'm going to present today is some work from our group at Sandia. There's a number of people who are contributing to this work. I work pretty closely with Eric Sear. We have a number of postdocs that are working together with us. And also a lot of the mathematical analysis is thanks to Xiaozhe Hu at Tufts. So I'll give a very short overview of some of our current work before I dive into this data-driven exterior calculus that we've been working on. So I think for this crowd, I think everyone's probably more or less familiar with physics-informed machine learning, but for the uninitiated, the way that we're thinking about this is we'd like to develop data-driven surrogates and models where it's just not tractable to derive a model from first principles. And so more classical models, right, you might derive a governing equation, it might have some material parameters that you need to estimate with basically at this point, very mature techniques. And there's been a lot of interest in the last few years to try and do some sort of black box learning, right? You take your expensive model, you plug it into TensorFlow, you see if it pops out a cheap surrogate. And what we're trying to do is something that's in the middle. So we don't know ahead of time what the model form has to look like, but we know that if you just do black box ML, oftentimes that doesn't work at all. You get something that's unstable. And so what we'd like to do is sprinkle in just enough mathematical structure so that you can guarantee that you extract a well-posed model, something that's physically realizable, and in particular, in small data limits. So some of the questions we've been looking at, this is kind of just like an advertisement for some other projects. On one side, we're trying to look at how to make DNNs work better, approximate better, train better. And so if you've worked in this area, you're probably familiar with the fact that you could throw a bigger and a bigger network at a, to try and solve a PDE, which is basically what we try and do in physics and engineering. But what you'll end up seeing is that you hit this optimization error. And so we've been developing architectures which give the same sort of convergence that HP finite element methods do, right? Which is really critical in order to be able to trust these things in high consequence environments. Another place we've been looking at is trying to extract constitutive relationships, in this case, equations of state for the Sandia pulse power, the Z machine. where basically we have outrageously high energy environments that we're using to test materials, and we'd like to extract relationships under these extreme environments where we really have no idea how to parameterize what's going on. So the talk today, what I'm going to focus on is the semiconductor physics problem that we're very interested in at the lab. For a semiconductor device, you can basically use what's called a TCAD model, which is a PDE model. It's a finite element, something you throw finite elements at, and it's very high fidelity, and it basically encapsulates all the physics for a single semiconductor device. So radiation, all that kind of stuff. The problem is that an actual system scale design is going to be made up of many, many semiconductors, millions at least. So what people do is develop what's called in the industry compact models, and those are just the circuits that you know from physics 1, Kirchhoff's law and so on. Basically what they do is they squint at this high fidelity solution, some experimental device, and they say, oh, if we stuck a capacitor here and a resistor there, and they empirically come up with something which is extremely efficient to simulate, and that's how they get to these larger scales in these circuit designs. But the problem with that is it's designed empirically. It takes basically a decade to do that, and you can only do that for these kind of nominal operating settings where you just design for kind of an idealized setting. So what do you do when you have something like radiation effects? These circuits are going on satellites, they're interacting with radiation in space and so on. And what we'd like to do is take that kind of decade-long empirical development of models and accelerate it to something that's on the order of months. So that way you can handle devices are made out of new materials, radiation effects, and so on. And so an exact treatment of physics and a guarantee that these things are solvable are critical for these kind of very high consequence problems that we're considering. And so the state of the art right now is physics informed machine learning, which is, I do a lot of work with pins and those kind of related ideas. They're very useful for a certain class of problems. And the idea behind them is that you have this hybrid PDE discretization / data assimilation, right? So you have your data that you'd like to regress in a deep neural network model for, and then you have this kind of wish list of all the extra properties you'd like your surrogate to have. So it might satisfy a certain PDE, it might satisfy boundary conditions, initial conditions, conservation principles, and so on. So the challenges to that are, first, these are all being introduced by penalty parameter. That's a lot of hyperparameters once you get to a complex system. How do you pick those? There is no theory behind that, and it's actually a little bit of a pathology. There's some interesting work coming out of Paris Perdicaris's group at UPenn, for example, looking at that. And even at best, if you can figure out how to set those penalty parameters, you have no idea. Basically, these physics are only going to hold to within your optimization error, right? So if you have some experience working with these models, you'll know that might just be like 0.1%, right? So for electromagnetics, fluid mechanics, a lot of these problems, we need these properties to hold to machine precision, right? So like electromagnetics, you have to have a divergence-free magnetic field to machine precision, or you'll get spurious waves in your solution. Similar stories in a variety of different disciplines. So this is the motivation, is we're trying to come up with something that really bakes these physics directly into the architecture, the same way, for example, we traditionally design finite element spaces. So the tool we're going to use for that are compatible spatial discretizations. These are kind of like the modern way of designing numerical PDE discretizations. And this is kind of like the bread and butter from the electromagnetism world, there's these kind of ideas. And in general, the way they work is they're tied to the Stokes theorems, right? The Gauss divergence theorem, Green's theorem, and so on. And they're preserving some sort of topological structure in the governing equations. And by doing that, they mimic properties of continuum operators, and that's why people call them mimetic discretizations. And I'll talk a little bit more about what I mean by that. So for these methods, there's two key ingredients. There's a topological structure, right? And classically in this PDE world, what that is a mesh, right? So that's cells, faces, edges, and nodes. They're all linked together with a boundary operator, right? Faces are the boundary of a cell, and so on. And so what we're going to do in this machine learning world that we're finding ourselves in now is we're going to use a graph as an inexpensive, low-dimensional surrogate for that mesh, right? So that's going to be something that gives you topological structure, but it's a lot smaller. It's a lower dimensional object to work with, so it'll be cheaper and efficient and so on. The second thing that makes these methods work is a notion of metric information, right? So if you think back to the Gauss divergence theorem, right, you have this topological operator, right, which is you just sum all the fluxes that are in the boundary of a cell, right? What makes this converge to the divergence is now you bring in the measure of the cell. This is a very low order, simple example. So this is the second piece, and graphs are missing that metric information. So what we're going to do is, right, so graphs are purely topological. Like in general, they're not even embedded into physical space, right? So they're just something about connections. So what we're going to do is we're going to machine learn this missing ingredient, the graphs lack. Okay, and so the ingredients, these are the pieces that make this stuff up. It's a little bit complicated, so I'm just going to explain it at a high level, right? You start with a chain complex, right? And in the PDE world, this is the mesh, cells, faces, edges, and nodes. For a graph, these are k cliques, right? So nodes are 1 clique, edges are a 2 clique, and so on. And so that's how we're going to replace that. And this has a property that the boundary operator of the boundary operator is equal to 0. And that structure is going to propagate through this whole construction. And so the next ingredient is a cochain complex. And so those are numbers attached to these traditionally mesh entities, right? And so that would be like a flux that you would attach to a face. So we'll attach numbers to these graph objects. And then what people typically do is they have codifferentials. And what these are you engineer, right? You design an inner product space. And this is a set of operators which are adjoint to these things with respect to this norm, right? So this is a little bit abstract, but to make it concrete, right? This cochain complex, right? All of these derivative operators that you get are your the divergence operator from the Gauss divergence theorem, the curl operator from the circulation theorem, right? The codifferentials are the adjoints of that, right? So if you have a divergence, this gives you a gradient and so on, right? And so this is the way we're going to come up with the graph version of all of these objects. And so what you're left with, right? If you haven't seen one of these commuting diagrams before, they're a little bit overwhelming, but it's actually pretty simple. So along the center line, you have the traditional graph calculus, a graph grad, a graph curl, a graph div, and the curl of the gradient is exactly equal to 0. The divergence of the curl is exactly equal to 0, right? And so what we're going to do is the way people typically derive these adjoint operators, right, is you just pick the correct inner product space to work in, right? So in the finite element world, that's typically you're working in L2, and so you just use the natural inner product in order to get your adjoint operators, your weak gradients, your weak curl, and so on, right? And so what we're going to do instead is we're going to introduce this learnable inner product, right? So this is going to be a diagonal matrix with positive entries, so that way this is positive definite, and that induces a learnable inner product. And what that does is it takes this graph calculus, this div grad curl, which doesn't actually converge in a meaningful way to vector calculus div grad curl, right? And we're going to bootstrap it. So we're going to parameterize the graph calculus into something that you can actually that can recover the vector calculus that we'd like to model physical systems. So this is a little bit abstract. It's a little bit painful if this isn't your background, working with this kind of like differential geometry stuff. Right, but it gives you something very, very practical. So it gives you learnable operators which locally and globally conserve fluxes, circulations, and potentials. Right, everything's tied to a Stokes theorem, so everything is exactly conservative at a local level. This gives you a theory for building invertible Hodge-Laplacians. Right, so that's like Darcy flow, magnetostatics, these kind of building blocks that make up fluid flow, solid mechanics, and E&M. And so you can mathematically prove that whatever model pops out of this, it's invertible, it has a Poincare inequality, and so on. And the most important thing is that these calculus operators that we've extracted have an exact sequence property, which means that the divergence of the curl is exactly equal to 0. The curl of the gradient is exactly equal to 0. That gives you what's called a Hodge decomposition. And what that lets you do is it lets you handle these non-trivial null spaces that pop up all over the physics world. Okay, so and just to say, we have the analysis to back this up. Okay, so that's a little bit abstract. So what I'm going to do now is I'm going to make this very concrete. So let's say you want to develop a surrogate for Darcy's equation, right? So you have a divergence of a bunch of fluxes is equal to a source. This is your conservation statement up here. Down here, you have your fluxes, or it's a gradient flux, right? So this is a diffusion process. And this top equation is what encodes physics, the conservation structure, and so on. This bottom line is what encodes the empirical relation, the closure, right? So every discipline all across physics, there's Fourier law, there's Ohm's law, and everyone has a different way of calling this kind of gradient closure. So what we're going to do to develop a surrogate is we're going to reach for the corresponding graph operator. So in this case, there's a divergence. So I'm going to take this parameterized divergence operator, and this is going to encode conservation structure. And then for our fluxes on the graph, what we're going to say is we have a gradient flux, right? And if you're familiar with this kind of language, you might recognize that in this very simple case, this reduces to a resistor network model, right? We're learning on a network, we're going to be learning effective resistances to represent this conservation law. But then what we can do is we can add a neural network to the fluxes, right? So we're just going to stick that black box piece into what's empirical anyway, into this description of fluxes, which will have some benefits later on. So the way you would use this is you have a high fidelity PDE. It lives on a very large mesh. One way that you could do this is you apply a coarsening. So we're just applying METIS, right? But something that's going to take that mesh and break it up into subdomains. And then that gives you your graph, right? And what we're going to do is we're going to train this model so that it can reproduce the integral moments of this high fidelity solution on this graph. Okay, and so this generalizes to more complex models of the same form, but all of them work the same way, right? You have a conservation statement, and you have some gradient flux plus a neural network parameterization. And so what you can show is this admits a variational interpretation, and you get an invertible bilinear form. This is what I mentioned about the Hodge-Laplacian, right? So this is something that is symmetric positive definite, and we have a Poincare inequality for. And then we have a nonlinear perturbation of that, right? And so this is the model that we want to fit, and we're going to set that up as an equality constraint optimization problem. And again, right, this is exactly enforcing physics. So even if you have one data point, you're going to get a model that is solvable and conservative to machine precision. Of course, probably won't be a very good model because you don't have much data there. But the point is that we don't want to mess around with these things that are tied to physics. Okay, so is this PDE constraint well posed? Yes, so you can prove that as long as the diffusive part, right, this Laplacian is big relative to the nonlinearity, then you can prove that this system has a unique solution, and that means you can always solve this equality constraint, right? And it really just comes down to some very simple bounds. I already claimed that this Laplacian has a Poincare constant, and then you're just going to relate that to the Lipschitz constant on this nonlinearity. Okay, and so this is maybe standard throughout the neural network literature, but it's pretty easy to get a bound on that Lipschitz constant. It's basically just a question about the width, the depth of the network, if you're using a deep neural network there, and so on. Okay, and so if you wanted, you could actually impose this during training. You could add this as a constraint to guarantee that you actually always get something well posed. In practice, we don't actually have to do that. We find that it steers us towards solutions that satisfy this constraint anyway. Okay, so now how are you actually going to solve this? It actually looks exactly the same way as most inverse problems in the PDE world. You solve a forward problem in order to get, for the current model parameters, what is the prediction? You solve an adjoint problem to get some Lagrange multipliers. And then what we're doing, because it's actually a relatively complex graph neural network that is encoding this model at this point, right? So we just take a single step of gradient descent, or a first order optimizer. We tend to use Atom in our work. And so that'll update the model, and then you repeat this whole process over and over again. So that'll give you, at every step, you'll always have something which satisfies the forward problem, and then you'll do a tweak to the model in order to update it. So let's just look at how it works for Darcy. For now, I'm not going to include the neural network because this basically looks like a normal PDE discretization. There's nothing crazy going on here. And so in this left column, this is a co-volume method, a staggered finite volume method, and you can think of it as a high fidelity solution. And what we're looking at is how the prediction, in terms of the number of subdomains in this data-driven model in the middle column, how does that compare to the same number of actual elements? And what I'm plotting to the right is the pressure profile from bottom left to top right, where green is the correct solution, blue is the data-driven one, and orange is the forward simulation. And kind of course, the forward simulation on a coarse mesh gives you a bad answer. Eventually, for many, many elements, now they start to sink into the correct thing. But what we see is that we've got, just with something super coarse, right, like a 3x3 mesh, if you want to call it a mesh, right? We're getting something that reproduces the solution well. And if you actually look at the training error for this, you can get the training error down to machine precision. So for these kind of elliptic problems, without any nonlinearity, you can get the training error to basically match the data set. So now let's add a nonlinearity. So what we're going to do is we're going to have an inclusion in the middle of the domain, which scales with the size of the pressure drop. So what that means is as you apply, it's getting more and more conductive as you apply a larger and larger pressure drop across the domain. And so the neural network is able to pick up, it's able to interpret this as just a nonlinearity in the governing equations. And now we've got a surrogate model, which is conservative, has all this nice structure and so on, but it's guaranteed to be solvable. Okay, so for Darcy, that's actually not, I mean, it's kind of interesting, but there's plenty of ways to do Darcy, and people are actually doing it with pins and things like that all the time now, and traditional inverse methods. So for magnetostatics, on the other hand, that's something that is really, really difficult to get correct, right? So I'm gonna look at an analogous problem, right? The permittivity now, which is the diffusion coefficient in magnetics, is going to scale with the magnitude of the magnetic field around the outside of the domain, right? And so this is a plot across this dashed line down here. Dashed is the training, the solid is the model, and you can basically nail these, the high fidelity solution, right? So what you've pulled out is a surrogate, which is exactly divergence free. It can handle sharp interfaces without any ringing phenomena, oscillations in your material properties, conserve circulation. It's guaranteed to be solvable, and it generalizes, right? Because we're not learning a response surface. We're learning an actual PDE model that you can just apply different boundary conditions to, right? And so really what this is giving you is a Dirichlet to Neumann map of a multi-scale system, right? So the direction we're taking this work is how can you embed this into a finite element simulation, right? This is kind of the perfect way to take something, a description of a microscale with very small scale structure, and extract a structure preserving surrogate to couple to the continuum scale. I mentioned the semiconductor problem. I won't really get into this, but this is an area where we're using this right now. And so the high fidelity PDE is you have to solve the drift diffusion equations, which I mentioned. And so these are, the y-axis is current, the x-axis is voltage. And what you see, and the left is a log scale, the right is a linear scale. What you see is there's this transition from exponential behavior. The labels got garbled, but this is basically 15 orders of magnitude, right? So for under a volt, you get something like 15 decades of data, and then it transitions to this kind of linear regime. So typically what people do right now is model this as an ideal diode. They have to empirically switch over to a resistor model and so on. And so in this framework, you can basically get a model that seamlessly handles these two regimes that are kind of difficult to handle. And this thing, right, because it has all these guarantees attached to it, you can just embed it in a traditional circuit simulator, right? And so we're we're using this as a way to generate models that can be coupled, brought into an existing, like, very mature circuit simulation framework. So these are my conclusions. We've presented this kind of mathematical framework for exterior calculus. This is something that's very general purpose and abstract. You could use this in all sorts of settings. But like I mentioned, I think the most immediate place where this is going to be useful is developing multi-scale models, right? Because we have this parameterization of a Dirichlet and Neumann map, right? And in a certain way, this is a lot like a reduced order model, right? Like you're extracting a cheap system that you can solve, and it's meant to encode some of the information about a higher fidelity thing. But in a traditional ROM, right, that's tied to a variational setting, right? You're doing PCA or however you do it to generate your basis, and then you stick that into a variational, like a least squares system and so on. And so those methods have a lot of trouble with structure preservation, right? Like, so if you're looking at Stokes flow, for example, you do PCA, you get a velocity space, you get a pressure space. How do you guarantee that those two spaces satisfy an if-SOP condition? There's all these kind of issues with structure preservation that are attached to ROM models. So this framework it's functionally it's similar, but it's tied a lot more closely to like a finite volume method. It's really designed to preserve this structure and get conservation correct. Also, we're working on a ton of projects right now at the lab. Some mostly much more applied than what I presented today. So if you're interested in any of these areas, please feel free to reach out to me, and I will stop here and take some questions. Thanks.
So, sorry, I think there's some internet instability. So is there any question from the audience? You can either speed up, unmute yourself and speed up, or you can type it in the chat room. So Nathan, I have a question about the graph. During the simulation, is the graph going to be constantly updated, or is going to be static, like a partitions problem?
Yeah, that's a great question. So right now, in what I presented, it's a static graph. We have a pre-processing step. We were just doing METIS, and that gives you, we've been calling it a model backbone, right, or a skeleton that you're going to hang these conservation laws on top of. In that case, it's static. We've been looking at some more sophisticated ways of doing graph partitioning that are tied to error estimators. You can do some spectral graph partitioning ideas in order to get something that's actually tailored to your solution to give you something better. The thing that I'm most excited about is, I think I referenced this paper at the beginning, this partition of unity networks. So we've been developing a way to learn a data-driven coarsened mesh kind of on the fly. You can use, classifiers are great for learning probability distributions. You can interpret those as a partition of unity, and then you can slap a polynomial basis on top of that. So we're moving toward this kind of thing where you're both learning the network topology and fitting the model on the fly kind of at the same time, but it's more complicated.
Yeah, I was wondering whether it's possible that you have a very fine background mesh or background graph or whatever, and then you think about how the subgraph, generating the subgraph and then condense it into your nodes, so that you can just think about it as a subgraph generation problem.
Yeah, for this one, the way we have it set up, that is the way it looks, right? And that is what we're doing when we're using METIS. It's doing a graph coarsening under the hood.
Yeah.
But yeah, to me, that's like the most exciting part of it. All the exterior calculus stuff. Once you have the chain complex, it just works on its own. But that's the part that I think is there's a lot of really interesting and creative stuff that you could do.
I also have one more questions about the graph calculations, and correct me if I'm wrong. Do you actually compute the solution at the nodes of the graph first and then project it back into the Euclidean space, or somehow try to map it, or so how do you connect the solution from the graph to the solution back into the spatial space? So that
So
part.
the only thing that it's trying to do is it's right. So we, for each node and edge, right, that corresponds to the cell, the average cell field, the average fluxes here.
Yeah.
It's the only way it's learning anything is just it's being trained to reproduce these moments from the fine scale solution.
Okay.
So that's, you know, that's where it's getting connected to reality from this kind of topological setting.
I see. Okay.
Yeah.
Okay. Thank you. Let's friend our first speaker once again, and then and thank you for keeping it on time. It's very important. So and we have our next speaker, Professor Wayne Kem Liu. I think we need no introductions for Wayne. And he will talk about hierarchical deep learning neural network for science and engineering simulation and design, proposed AI framework for science and engineering software. Thank you, Wayne.
Okay, thank you, Steve. And do you guys see my screen? Okay, so I will just give a brief introduction of the I have something is wrong here. Can you guys mute if you can? Okay, so I will talk a little more about what I call the hidden, called hierarchical deep learning neural network. Okay, and this is done by a lot of collaborators listed here. And I will start give you a short motivation what we are doing, and then I will talk about the hidden method. And most of you might be familiar with finite elements, so I'll go degenerate this one to the finite element method. And you can also degenerate any other interpolants, okay? And then we talk about some reduced order model on, you know, using something called the proper generalized decomposition. And then I will talk about another reduced order model using, you know, some mechanistic based type method. It's called hidden SCA, hidden PGD. And then I'm going to show you three classes of problems that I want to solve using this general neural network hidden. The first one is mechanistically insufficient problem with data. And the second would be purely data-driven problem. And the third type would be computationally expensive problem. So these are three classes of problem that we can solve using this kind of network. And I will give you the future outlook. Mostly try to expand this to optimization and design. So our goal here is to combine AI, which I call the hidden AI, together with the ICME, which is called integrated computational materials engineering. Okay, and the whole idea here would be, we have been doing a lot on, you know, ICME. And also there are a lot of research work now doing AI. Can we combine them together, right? So I call this mechanistic data science, you know, for engineering, because the mechanistic is the ICME, basically based on some mechanisms. And the data science is the AI. And so basically we leverage the principle of mathematical science and I break it down into the 6 steps. The first thing will be multimodal generation and collection. So how you're going to generate data from experiment and also from simulations. And then based on that, there's so much data that we cannot do every one of them. So we're going to extract mechanistic feature based on some, say, signal analysis, image analysis, or, you know, digital analysis framework. And then we're going to do dimensional reduction. That means we cannot solve all this equation. It's so huge. So dimension reduction, such as PGD or what I call the SCA, would be very important in this case. And then we try to do something called the reduced order circuit models, because now it's the reduced order model. And the question would be, are they the valid one? Even though we have some data we can calibrate on. Okay, so that's the reason why it's not the exact model anymore, it is a surrogate model. And finally, we want to use machine learning to do regression classification, just to see how good our model is. And so I said earlier, I'm going to solve 3 kinds of problems. mechanism insufficient problems such as additive manufacturing. This is a pretty new area. And the second one would be pure data-driven that we are working on is the fatigue problem, because this takes a long time. It's very hard to do experiment. And the other one is a multi-scale problem, which is very expensive to solve. Okay, so let me talk about the universal approximation. Basically, it's a neural network, which consists of the input layer, and the hidden layer consists of neurons, and the output is the output layer. Okay, and the whole goal here would be you are looking for the very general approximation function, which is the input. In this case, just using X and Y, the weights and biases, and the activation functions. Okay. Now, what I'd like to do here would be, I want to write this equation in terms of interpolation form. So it's still pretty general, but now you restrict a little bit on what I mean by the upper layer. Okay. In this case here, would be, you can have a very nice way to something that can be interpretable for the interpolation structure for the approximation functions, such as finite element, isogeometric, or other kind of approximations in this case. Okay. So I'll give you one example that we did for finite elements. So we constrained the weight and biases to be the input, mesh, or the measuring method would be meshless. It's just a nuclear coordinate. I call X star. And then by this, now you have the hidden, now put it into a more restrictive form called the interpolation form. Okay, that you can actually satisfy the finite element approximation, Kronecker delta, and the partition unity in this case. So that is something that you can see we started from a very general approach to something a lot more restricted class that we all know is the finite element for any dimension. It can be 4-dimensional space if you want. Okay, so you can think about what would be, if you look at approximation, neural network, or deep learning, a neural network is the biggest space, and the finite element is only a very subclass of this system. And then I'm going to refine a little bit more, called hidden. So now I'm going to let the X star to be a variable. That means in training these functions, I also want to train the position to give me better accuracy. So in this case, it is a lot better than the finite element method in this case, because I trained another set of variable, the X star. I want to do a little bit more called PGD. So I'm going to add in something called modal decomposition. And that's more or less the framework for the proper generalized decomposition. That will be a subset of this system, but it's a larger set of the finite element space. But if I take enough modes, or I can get back to the hidden framework in this case. Okay. So this is the class of method they're working on. And if you look at here, I can show that, would be the accuracy versus the degrees of freedom. So the whole idea of a neural network has a lot more degrees of freedom. So it's a lot more expensive, but it's more accurate. The hidden PGD is the less degrees of freedom. They might not be the most accurate solutions. Okay, so you have a choice of the different approximation in this case. So we're going to combine all this together. So I'll give you some idea on some theoretical study. Okay, and I want you to focus on would be for this problem, would be we have very little number of degrees of freedom compared to finite element. But if you look at the H1 norm, we can get better than the finite element already. So it's a very simple illustration of the problem. Okay. The other technique that we look for is called the physics-based reduced order model. So what I talked to you about is the mathematical based on projections there. Now this is called a self-consistent cluster analysis. So the whole idea would be we can start with a problem, say the microstructure model. We use the unsupervised learning techniques such as k-mean clustering or cell organization map or other method, group the points together. So you have to reduce model. But for this, I need to solve a green function, and I also need to solve a Liebman-Stringer equation to get a reduced order model in this case. So I call this finite element, okay, or hidden if I want to do that. I haven't done that yet, called SCA for n class of problem concurrently solve the system here. Okay, say for example, for this particular problem, it's a woven composite. You have an architecture woven system, which is based on like clothing. Okay, you can do knitting, all this based on composites, but many layers of this. So you can model this like a finite element, but for each material point, I have a woven composite structure. You can think about this RVE, okay? But at each of the woven, it's a makeup of the unidirectional system. And for the matrix, it is made up of a nanoscale or submicron scale matrix reinforcement. The key thing will be, can we solve this box here in a concurrent way so that we can do all the detailed calculation together? I think that is what the self-consistent cluster analysis that we have developed. Okay. So the whole idea, what the hidden is, if you look at the traditional approach, you can have a lot of different kinds of software and try to solve them separately, iterate among them. Okay. Now, you know about neural network is a big framework. So we lump all these green box into one with all the parameters. So of course, with the solution scheme need to be redesigned. I think the previous speaker had talked about how to solve this kind of system. And I think that is one way that we look for. But now everything is one neural network in this case. They are called the hidden reduced order model or finite element neural network in this case. Okay, so let me give you an example on this one here. Now we have space and time, that's the PDE, but I'm going to add in parameter space. It depends how you define it. And then you're going to define what the pre-processing function, okay? And the pre-processing function is to extract the mechanistic feature from the data. So that is the part that I talk about. You know, first of all, data collection, that will be input. And then the second thing will be mechanistic feature. That is what this function is. And then we talk about would be scaling layer. This is little new. And the whole idea, we want to do some kind of dimension reduction in this case here. Okay. And the dimension reduction, you know, would be very important because the system is too large. And then the next level I will talk about would be on this hierarchical deep neural network. Okay, then I'm going to link experimental data with ICME techniques. And the solution layer will be based on what type of equation you're solving, what kind of experiment you're going to do. And that's operation layer that I'm talking about. And finally is the loss functions. Okay, so that is something that you need to generate. This is a general framework that we're looking at. Let me just talk about the first type of problem called the mechanistic insufficient problem. The physics is known, but you need calibration. Okay, so you need to calibrate with the experimental data. You have the data, but at the same time, you need fast computation. I'm going to show you a couple of examples, 3 examples here. Okay, and the first 2 are mostly validated by the Air Force Research Lab AM competitions. And the third one, we just accepted a paper in scoliosis, which are biomechanical problems. So if you look at here, this is the hidden PGD approach. Is governed by this equation. Now we can add in experimental data in the system here. Okay, but at the same time, we also need to calibrate the system based on experimental data. So, like I said, we need to have done experimental data, and this is the AM bench leveraged by the Air Force Research Lab. And we won the first prize because we know how to do calibration. Then when we use the PGD. And the next time will be we do simulation, and then we do a blind test, submit our results, and we actually get the first prize for this one. And you can actually look a lot of physics by the minimizing or optimize the material properties based on the processing parameter in this case. So the impact of this would be we get the fundamental understanding of molecule dynamics and the defect mitigation. And you need the experimental validation inside this particular framework. Okay, the second problem I want to talk about is fatigue. Okay, so, GE talking about how they can actually do the 3D printing is a good news, but the problem will be is limited by data. So it's a data-driven approach. For them, they spend tens of millions to design display by doing one type of machine, one type of powder, and find out the optimum processing parameter. So if you change a powder, it's not going to work because everything, all the data will be useless. Okay, so we try to do combination on it. So we talk about would be when some of the data, we can do our experiment, but very expensive. And we also look for data from the literature. And the key thing I like to focus on is the data from ICME tubes. So for this, I come up with something called the mechanistic knowledge transfer. So that's the data structure of the system. You have a general idea on process directly to properties, or I can say process directly to performance. You look at data from literature, data from experiment, and we did some experiment ourselves, and the data from ICME2. So now our hidden framework reduced to this particular part. And this is some of the experimental setup that we have done. And you can see for each of this one has a different processing parameter. Okay, because the way it is the machine is set up for this particular 4D specimen. So if you look at the data, we have the black dot and the red dot. Those are actually from literature. And the blue dot, the purple dot is our own experiment. But here you have two sets of fatigue. One is called low cycle fatigue. And we don't have time to do the high cycle fatigue, but we do have the data from the literature. So can I use mechanistic learning, transfer learning in this case? So those are the data that have both low cycle and high cycle fatigue. And these are experiments only for the low cycle fatigue. And with mechanistic knowledge transfer, we can actually predict this. Now, we do not know the answer yet. We actually do prediction. Now we need to do experiment to see if our method is going to work. But you can see the R square keep increasing by more data in this case. So this is spine problem, is the scoliosis, the curvature of the spine. I will not go through detail how we calibrate. It's the same neural network. Okay. The whole idea would be this patient has a double curvature, and we have very limited data for this one. Okay, so you can see this is a data set that we have for 124 months. The training data set has only 4, actually including the first of 5 data sets, but we want to do the prediction, okay, based on something inside and something outside, okay. And again, will be with the mechanistic neural network, you can see the prediction inside domain and the prediction outside domain using this data set. And you can see here will be this our prediction. And the more mechanistic data in, the more accurate the solution is. But we can actually predict outside the range reasonably well. But remember, these are very limited data sets in this case. Okay, the second type of problem I'm talking about is pure data-driven problem. So I'll give you something called the dimension net. And then from also tell you from pure experiment, can I predict the mechanical properties, bypass the structure? So the physics unknown, we don't know the physics, but we need to do calibration. It's very important. The data available, we need fast computation. Okay, so this is our dimension net. Okay, the whole idea will be now we focus the spatial and time and the parameter. We come up with something called a scaling neural network. This you can think about a scaling neural network will be it basically is like a dimension analysis network. Okay, but then you need the data. So this is the training data, and the output, is what you're looking for. Okay, so the dimension is developed to reduce the number of parameters. So the whole idea was this is for design in this case. Okay, and I want to say will be if you input m dimension parameter, I want to have n. Okay, and n is very large, and I want to get the minimum number m in this case. Okay, so the potential application will be engine material analysis, I'm actually proposing to do for autonomous vehicles because there's so much data on it, advanced manufacturing and other applications. Okay, so give you this example here would be, we do a lot of simulation. This is done in the Argonne supercomputer. We input our own laser-induced vapor plume model into the ANSYS Fluent simulation dataset. Very expensive calculations. What we can done would be we actually discover a new keyhole number, which we submitted to Nature Communication. We get pretty good review. It should be accepted after revision. And we can reduce the dimension from 7 to 1, this number. Okay. And if you look at the other one, so what is the application would be look at from the simulation, you can actually now focus on the physics of the problem. I will not go through the physics on this one here. But the other one is porosity, which is the defects. Okay. We can actually come up with a new energy density parameter together with Q number, and we can reduce from 11 to 2. So this is a really powerful tool that we are working on. So going back to here, we do experiments. Okay, so what we like to do would be the temperature history, thermal time history is the most important data that we have. I want to measure a number of point two experiments. These are all experimental work. Okay, can I have limited data? Well, actually, I would not say it's limited, but it take about 2 years of work that we spent 2 months on designing, taking the data, but 2 months to design the experiment. Okay, and then now we're still analyzing data on this. So it's a purely data-driven analysis, and you can see the prediction. So now these are based on infrared imaging, and we can do some kind of prediction. Now then we can use it to calibrate our software. Now we can do a lot more flexibility. So that's what our hidden framework is about. The third type problem is a very computational intense problem. That means the physics is known, but you still need to calibrate a lot of parameters. The data is not available because these are design problem, but you need very fast computation. For this, I'm coming up with some kind of 3-scale composite material design problem. So let me just show you a little bit what it is. So I go back to the problem I'm talking about would be for a particular plane, we have a lap joint. These are typically done by fine elements, and these are governed by woven composites, or even braided composite. We're working on that right now. For each of these woven composite, we call it toe, is governed by the unit direction, and the epoxy design is something we are still working with the Air Force. And if you solve the problem, say I do say 1 million degrees of freedom for this one, I do maybe about tens of thousands degrees of freedom. So if you go through the degrees of freedom, I'm talking about fully strong coupling, okay, because we're looking for design. You're talking about 10 to the 25 order of elements. However, using the clustering technique, I clustered it in the 10, 96, and so forth. You still pretty big system. You still talk about order of 100,000 degrees of freedom. But now we can solve this, in a single PC or a small cluster in this case. So that is the approach we are talking about. So this is just show you the example on, how we do limited experiment calibration. They're all within 10% of the system. So we are writing interfaces to commercial codes, basically. Okay, let me go to the next one. So this is my final slide, actually, final 3 slides. This is the framework they're looking for. So instead of doing space and time, we have to prompt the space. It's a very general AI framework that we're thinking about. You can put this in terms of a generalized PDE, but this generalized PDE, we want to lump them together with experimental and calibrations, everything together. Okay, and the goal here is look at the size of the problem. If you just do the classical way, it's exponential. If you're using our hidden framework, it's linear. So that is the goal. Now, this is our claim. Okay, but it will take us more time to work on it. Let me show you, say, optimization. Okay, so this is the neural network that we come up with. And you can see here would be, if we put it in the hidden framework, you can see the solution time is much smaller because we don't really need that many, degrees of freedom to solve it. At the same time, it depends on what type of machine learning algorithm to solve the problem. We can solve it a little bit faster, but this is a very small scale problem. We just started working on it. And this is my final slide. We have a conference co-hosted by Professor Sun and Columbia and Stanford 6 University. Take a look at the webpage. We hope to see you there. Thank you.
So thank you, Professor Law, for Professor Liu for the wonderful presentation. So does the audience has any questions?
I have a question.
Mm-hmm.
Thank you. Wing, that was a great talk. Can you comment on, in particular for additive manufacturing problems where there's path-dependent history that comes in, can you talk about the way you're thinking about like physics preservation and what's important in order to get something that generalizes and is stable and all that kind of stuff?
Well, like I said, would be, the numerical method is very important, but to me, that is very small compared to the actual AM literature in this case here. Now we're using finite volume technique, okay? They have certain conservation properties, but we are not really focusing on that at this time because that error is very small compared to a lot of other things that you don't even know, okay? But the thing will be, if you have a better algorithm, I can take it in, but that is not our focus. Our focus is a lot more on the general framework of the algorithm is this one. Okay, so you're talking about a very small part of what we're interested in is this part. Okay, but there are a lot more things you don't even know about this. And we also talk about experimental. You need to do calibrations. So there are a lot of things that we want to focus on is on a much bigger picture, okay, on a system, but you do have data. The key thing would be make sure your experimental data is reliable. If they're not reliable, then it's no good. But at the same time, your computation, definitely the more accurate you have, it's just a matter of how detailed you want to understand the physics. But since we know the physics, we can actually do very simplified model to understand a problem within 5 to 10%. I think that is very good if you can actually predict something like this. Let me show you here. For this problem, okay. If you really look at the experimental data, the variation can be over 100%. So it depends on what your interest is.
Mm-hmm. Thank you.
So the audience also type one questions in the chat box. Let me read it out. So this is from Feruza. So how big are your data set? How long does it take to train the deep learning model? How constrained are embedded in deep learning models?
That is a very broad question. It depends on which part of the. It depends on which part of the system. Let me go back to this one here. For example, the calibration experiment, okay, for the additive manufacturing system I'm talking about, we try different techniques, in particular one here, okay, to give, they give us 11 track of data, which is very limited, okay. You can see the data is very, very rough, okay. And we actually we try different techniques to do the calibration. And it takes days at the beginning because we use genetic programming to do calibration. But then we use a reduced order model. Once we learn the system, it takes minutes. Okay. So it really depends on, we are still learning how to do this thing here. Data is the real issue. We don't have enough data for this kind of system. But I think will be that's the reason why we are looking in the mechanistic knowledge transfer to complement. You know, we have a STTR project on fatigue. The data is extremely limited because the data are not shared.
Okay, yeah. I have related questions about the data availability and the training. So I think in slide 21,
21.
21, it shows some progressive improvement when we extend the database. I was wondering, when you extend the database, do you also retrain the neural network, like finding different hyperparameter, and then we design the neural network, or this is coming from the same neural network submit to different data?
Okay, so we are working with the Children's Hospital, Laurie Children's Hospital.
Yeah.
We have supposed to be 154 patients. Okay, and each one of them take X-ray no more than 20 because you cannot take too much X-ray on it. Okay, but this involves a lot of details on it. We only look at 2 patients, only 2 patients so far.
Yeah.
Okay, because would be to get the data set takes months because it's not as simple as you think. Okay, but if you're really interested in this, you should take a look at the reference I gave you. This paper. So this is online already. You can see how complicated the problem is. Okay.
Okay. So for the interest of time, I will just repeat one last questions and then we will move on. So this is from Alberto. So great talk. In the composite example, the high DNN framework is able to account for cohesive failure between fiber and matrix, or between layer like denominations.
We actually account for all the details, but I don't have time to talk about it. We can account the detailed geometry of the woven composites, the detailed weaving conditions. Okay, and this is a separate talk by itself. We can account for all the details. These are mostly unpublished work because we're filing a patent on it.
Okay. So thank you, Wayne, again.
Thank you
for giving the time to us. We will move to the next speaker. So our next speaker is the experimentalist. Professor Eddie Keaton. He is going to talk about his work on a digital image-based experimental mechanics to understand mechanics respond under extreme conditions. So thank you.
Well, appreciate it. Thank you so much for having me. And it looks like it's odd that I'm presenting experimental work here in this highly mathematical and machine learning.
But I think it would be, sorry to interrupt. I think it would be great to have an experimentalist in the team. Let me, because I was thinking before we start, sorry about that. It would be great. Yeah, so we would like to have an experimentalist in the talk to give us different perspective about the demand or the available data, so that we can have a cohesive theme on not just creating the model, but what kind of demand in the upstream that can help us create a better framework. So sorry about the interruption. So Eddie, I will give the stage to you. So I will mute myself. Thank you.
Oh, no, I appreciate it. Of course, I like it, and I'm enjoying the talk, and this gives me an exposure to the other world, and also.
And also, so Eddie, sorry, can you switch the presentation? Right now, we are seeing the 2 slides. Can you switching the main slide?
You can't see anything?
I can see the slide, but I see the slide with the preparation. In the PowerPoint, you should be able to swap that into the main screen. Yes, yeah, and then can you go to the full? Can you go to the full slide?
That's what I did. Let me see. Can you see it now? The full slide?
I
No.
can.
Okay. No, it's still showing us the PowerPoint. So either go to slideshow and start, or your other presentation you had?
Let me, I have two screens, so that might be the problem.
Yeah, I think that we are showing the secondary screen. I think you just need to go to slide, and then when you go to the full screen mode, there is a ability to switch. If not, I think this is also fine. We can go forward with it.
No, I'm going to do that again.
Okay, thank you. Thank you for the patience.
Can you see it now?
We see the PowerPoint. It says digital image-based experimental. So right where you have, all right, so then there should be a white toolbar on the very bottom where it says slide 1 of 27. If you go to either the screen so we can just see the current slide.
Yeah, I think go to the displacement setting on the top. So can you put your mouse into the display setting on the top? Okay, yes, perfect. Thank you. Yeah. Please unmute. So Alice, can you unmute yourself? So there are no audio this time. It was working before. So Alice, can you try to say something? Yeah, I cannot hear you.
Can you hear me now?
Yes, yes, perfect. Yes.
I'm really sorry. We tried it before the session started, but somehow
Okay.
I got it.
It's okay. Let's start it this way. So.
Okay. I'm going to present my work on digital-based experiment to understand materials under extreme environments. And this was the outline I'm to talk today. I would briefly say about the digital image correlations, and I will show you some of the work we did in our lab. There might be a question why we're interested in extreme environments. There are two major goals here. One is to understand materials so that to design a structure that can resist such adverse condition. As shown here, steel was designed by Army research office that can stand high temperature environments. And also the other side is to handle materials safely, especially explosives as shown here that happen during transportations. So the way we do in our lab use digital-based experiments and digital image correlation, since if you don't know, I will just briefly introduce you how it works. You have a specimen that is speckled in a pattern. In this case, it's white and black dots. And you have a specimen that been under loading and take image starting from reference image before load happened, and subsequently take image while loading. Then you can track each point or position to find displacement. Once you find displacement, you can calculate strain, other conditions. So of course, tracking one point is impossible in this type of experiment, but you can track subsets, and you can use different matching algorithms to find the position of that. You can do it in 3D. If you have two camera system, you can get the full field information, including the outplane deformations. And just to say, this technique started in late 80s and just originated at the University of South Carolina, now being used in many places. So some of the example I'm going to show you that are not new to the community. For example, cellular materials under impact loading conditions. These materials are known for energy absorptions and applied for structures that subjected to high strain net loadings, such as Navy ships, helmets, and others. The reason why these cellular materials, they have a large deformation and they have a large area where they can absorb energy. And there has been a lot of interest in developing such materials with higher yield stress, but also increasing this energy absorptions. Unfortunately, these materials, so far until today, even though there are a lot of computational as well as experimental techniques, the practical design is based on empirical formulations. The reason why is not as simple we think that to understand these material behaviors. From experimental perspective, these cellular materials are low impedance materials. That means the material response under impact loading condition depends on the propagations of stresses. If you see, for example, the video running here, you impact this side, there is a large deformation in the left side, whereas the right side don't see anything until the stress wave reaches that side. So if you see in the right side, where you have digital image correlations image shown here, there is a time between each position where the strain reaches that positions. So the traditional way of measuring this response by having load cell on the backside or other methods doesn't work because of the material response is not uniform in this case. So in our lab, you use these digital image correlations to measure these deformations under different loading conditions. So what we do use, rather than relying on this the quasi-static equilibrium conditions, we wrote the dynamic equations, including the inertia term. And as you see that if it's uniaxial compression loading in the absence of body force, you could have this. If acceleration 0 and the quasi-static will be sigma z will be uniform. That means the stress are uniform in this side. If it's dynamic conditions, your stress at any position depend not only the stress you measure on the backside, but also depends on the inertia terms. So having this inertia term is important if you want to measure the stress response of this material at high strain with loadings. So use this digital image to measure this one. So what we did is the inertia, the integral term is a function of density as well as accelerations. The density changes as the loading because of this is material is compressed. We have a model that relates your density at any time in positions with a function of initial density and some terms. This exponential term actually related to the strain in z directions and the Poisson's ratio. The good thing about this digital image correlation, we can measure strain in all directions. That means I can measure the Poisson's ratio and the strain in this direction. So I can calculate or measure this exponential term, and I can update my density at any location along this specimen. And the acceleration term also is actually can be found from the displacement measured from digital image correlation. Basically, all except the last term, dz, can be measured with digital image correlation, and I can update and get my stress strain relations in this. So this help us to do experiments at any strain rate and measure the response, including the inertia terms. The other things, you can use these digital image correlations. Now, having that my stress is formulated from displacements at any locations, basically I can measure the local stress strain response in these materials. So to show this, what we did, we ran an experiment in a shock tube where a large projectile hit this foam materials, and we're able to create sort of strain rate difference across the specimen lengths. So that means your specimen not only subjected to impact loading, but along your specimen direction, the strain rate is also different. So based on that, we can measure actually from one experiment, since we can create a range of strain rates along the length of the specimen, we can calculate the stress strain response at different strain rate based on one experiment. This is a stress this time as a function of time at different location and strain, and this is strain rate. Having this the full field measurements able us to understand this stress strain response of these materials, but cellular materials, they are actually materials that made of some parent materials which has specific property plus geometric factors, and their failure mechanics or their failure mode depends on the geometry too. So under quasi-static, there is a well understood that the failure modes at cellular scale can be actually calculated based on the parent materials as well as some geometries. For example, you can say this is based on elastic buckling or pore collapse or brittle failure. This is recorded in the Ashby book. Unfortunately, in order to understand this under high strain rate loading condition, you have to use some sort of either modifying this or have other way of understanding what is the local failure modes under high strain rate loadings. Some researchers have updated the strain rate response of the material, the parent materials, as shown here in this paper, and use this elastic response at cellular scale under high strain rate. What we found in our study that having this digital image correlation experiment at small scale, what we found that the local strain rate actually in this material are not the same as we think in the continuum scale material response. For example, in this curve, what we showed that this is the global response, strain rate response. If you average the whole specimen, this is the strain rate you get around 2000 under these impact loadings. But if you focus on local region and measure the strain rate on that region, it could be as high as one order magnitude compared to the global. So if the strain rate response is this much different, you cannot just simply update the strain rate of the parent materials and use to find the local response of these materials. So this tells us they need another way to understand these materials under high strain rate loadings. So we start our own finite element models using these cellular models, Voronoi models. Our objective is to understand this material and their response and try to optimize their configurations, so in order to absorb more energy in terms subjected to impact as well as shock loadings. So the reason why we say that, it's well documented that the response of this material highly depends on the density of the parent materials as well as the relative density. So having said this, if we can optimize the way these cellular materials are arranged in one material system, we can increase, especially in case of high strength loading, can increase the energy absorbed in these materials. So using our finite element models and digital image correlations, we try to match first how the material responds for homogeneous materials and start using graded material systems. So these are our models that shows where the materials are under impact when the different cellular materials are being used. In this case, for example, we use two material configuration. One is stiff cellular materials. The other one is more compliant or the softer materials. So the material response graded from one direction to the other directions, and we subjected load in different directions. The one in the left side, you can see that that is the rigid side had been impacted, and the deformation happened as well as in the right side. You can see that the right side had been also started deforming. When you increase the velocity of the impact, you would see that there will be a response from the right side that interact with the stress propagation from the left side that actually changes the way the material responds. On the other side, if you hit the specimen on the softer side, you will see only one type of deformation. So by changing the way this are arranged, we hope to find a better configuration to absorb more energy. So experimentally, what we did, actually, we used 3-layer systems where we have cellular materials with different densities. They are attached together, as shown here. So the one side, on the left side, is the softer side being impacted. On the other side, the stiffer side being impacted. And you can see exactly how the response is different in this case. So in the first side, the softer deform first, then the second layer and the third layer. That's expected. But when you see it on the other side, this is the stiffer side. You impact this side, but the deformation happened on the other side. And you can see that the deformation interactions. This, this gave us an idea that the material response can be just tailored by reconfiguring the cell structure of these materials and try to optimize this. So this is ongoing research, but that's what we're doing. The main challenge what we have here is there are a lot of variables that use density, relative density, strain rate, impact velocity, and you need a lot of experiments, hundreds, if not thousands of experiments, if you really want to understand at different strain and different variables. And also the length scale. So local strain is completely different than the continuum response and how you relate to this. So the opportunity is the experimental technique is being advanced, and we are able to measure strain at local strain as well as the continuum scale. But also is the opportunity that some of the physics-based machine learnings, and I think some of the topic we heard today that are encouraging that can be used to optimize these systems along this. Another experiment that being used for on this digital-based mechanics is on the microstructural response of magnesiums in this case. So the objective, you probably knew that there are a big interest in the movement that to design materials based on their function. So what we call is materials by design, rather than using and modifying the current existing materials, but can we design materials? For that, you need to understand the current materials at different length scale. And in our experiment, what we try to do is understand magnesium and how they respond under different loading conditions at local scales. Of course, magnesium are used for aerospace and the other industries. And if it's pure magnesiums, it's HCP type metal. They have very limited active slip systems, and they are brittle. And we know that. But based on our experiment can we understand how the configuration or the orientation of the grains detect the response, and how the strain rate also affecting this. What we did is we took the pure casted magnesiums and we could specimen at different orientations. If you casted material like this, you could have specimens that the grains are arranged horizontally. You could have grains arranged vertically, and you can also grains that are somehow, isotropic type configurations. We use both quasi-static as well as dynamic experiments. So this is the microstructures looks before speckling. Then you speckle that and do the experiment. When you subject it to the experiment, this is a digital image correlation, full field displacement in the strain fields. What we found that actually the global stress strain response is pretty much the same, except small changes at initial. It's the sample which has the grains are in vertical direction high, a little bit stiffer than compared to the others. Otherwise, the response is somehow similar, but we clearly show that indeed in the quasi-static conditions, the failure that happens, especially the crack happens in the grain boundaries. That's we showed it here. It's very clear here. As you see, this is a quasi-static and this is a dynamic response. In the quasi-static, of course, the response is heterogeneous. Again, initiation occur in the boundaries. And this can actually qualitative and quantitative confirmation of this big weak boundaries in the quasi-static conditions. We observe also in the dynamic case that the triple junction points receive high degree of localized activity. You could see that, when three grains are joined, that's where you see large deformation mechanism. Also, if the grains that are adjacent to the large grain shows very little axial deformations. We also able to measure rotation. You can see this is a rotation of the strain. We measure the rotations on the grains that show that again the triple junctions points show high degree of rotations, and this also implies that there is grain boundary sliding occurring in these materials. So this is just purely based on these correlations. We also try to understand how the grain actually participated in the deformation mechanics. So one thing we try to do is we try to separate the grain strain on the grain versus on the inside the grains. So first we try to identify what is the grain boundaries, and that the grain boundaries we use the digital image correlation again. We use two strains and separate the position where the strains change, and you can see that this is where we show in the AX and AYY, and literally you can see that there is a big jump where the strains are changing, and that's where we found that this is the grain boundary. Of course, this is not the grain boundary that what materials use for studying diffusion. This is just a way to qualitatively or quantitatively assess the movement of or the strain in the grain as well as inside the grains. So we separate this grains strain in the grain and the boundaries, and we showed that for dynamic as well as quasi-statics, what are the response of these materials. So eta is the strain in the grain over the total. As you see that for different specimens, for horizontal, vertical, and equal distance, equal size specimens, the involvement of the grain boundary is different. As you see, the samples which has equal size actually has larger involvement of the grain compared to the others. But one thing which confirmed here in this, that the quasi-static has a large grain involvement than the dynamics. So it makes sense that the dynamic case, you don't have time for the grain to respond, and most of the deformation happen inside the grains, but in the quasi-static clearly show that the grain boundary has a a large deformation response. And this is, again, possible with this digital image correlation. The other thing which could be, this is my last one, is local deformation in energetic materials. In this particular is polymer bonded explosives. These are highly heterogeneous materials. There is a crystals embedded in the polymers, and their response is completely heterogeneous. There is a lot of interest to understand what are the deformation mechanisms, especially that leads to hotspot formation and leads to ignitions under low impact loading conditions. We use polymer bonded sugar. Sugar is a crystal, and this is a specimen. We made it here at the University of South Carolina, and we tested at different loading conditions. Of course, we were able to measure the heterogeneity of the deformations, but locally, what happens on these materials? And one interesting thing we found in this case, in addition to the local heterogeneity deformations, but we were able to measure the rotation of the crystals inside this material that actually changes how these materials behave under dynamic conditions. I will talk about this rotation in a minute and what that could be, what implies. So these materials, usually they fail by shear banding. And as we know, shear bands are formed when mechanical response of the material decreases with increasing deformations. In most metals, they go large deformation, but unfortunately, in this material, the shear band happens at low strain, and we're trying to see what causes shear banding. We use this local DIC. This is very small DIC in the order of 10 microns per pixel. And we are able to measure actually not only the heterogeneity, but we are able to measure the strain on the specific grains inside these materials. And what we found in our paper, that the shear band actually in this PBX is formed with two main mechanisms. One is due to thermal softening of this highly localized polymer deformation, and also the mechanical softening due to the damage accumulation in the materials. What we found for crystals that are small, there is a large deformation going on that also contributes on this shear banding formations. The main actually interest in this topic was funded by Air Force was to identify what are the hotspot formation mechanism in this. There are a lot of research, theoretical as well as experimental study to understand what causes these hot formations. So in this case, we did a synthetic experiment where we have a polymer binders, which has different scenarios. In the first one, we just heat the polymer binder and measure the temperature, what happens. And the second one, we had a small hole that subjected to under impact loading and to see if there is, again, temperature localization. And we add one graphite rod on this case and also measure that. We had 2 graphite and 3 graphite. So we did a lot of experiments to see what is the main cause that increase the temperature in this material. And we use this high speed infrared imaging to measure the temperatures. So what?
And
Yeah,
do you think you can finish in?
Yes, I am done.
Mhm.
So what actually happens that the rod which has 2 crystals has the largest temperatures, and we found that indeed actually the temperature rise is not because of the deformation, but it's because of frictions. And I told you earlier that we measure this rotation of the crystals that actually happen in this material. So that is actually the main cause that increase. So this rotation increases at sudden at these positions. So this is just explaining what happened on these 2 rods, but I will stop here